All right, guys. Topic 3 here, or 3.1 to be specific. Here's sort of an introduction to thermal physics. First things to cover, molecular theory of solids, liquids, and gases, temperature and absolute temperature, that is Celsius and Kelvin, internal energy, specific heat capacity, and heat capacity. Some key terms there. All right, solids, liquids, and gases. This shouldn't take us long because if you're watching this video, you probably have already learned this at multiple grade levels. Prior to this, we've seen this famous sort of concept of solids, liquids, and gases, where we have solids, much tighter particles, and their structure is solid. It does not flow. If you put solids into containers, they do not fit the shape. They simply will sit there unless it is obviously something granular like sand. They're difficult to compress and they're generally quite dense. When we talk about density, remember that density would be equal to mass divided by volume. So having a large density means you have a lot of mass in a small amount of space or volume. So just keep that in mind. When you think of really dense solids, you think of things like iron. Iron definitely would sink to the bottom of a pool. It would not float. Things that are less dense have a little bit less mass per volume. Things like wood might float, things like styrofoam, etc. Liquids can flow. We say that liquids are a fluid. Liquids and gases actually are both called fluids. They can flow. They're generally dense. We say that they're not as dense as some solids, but they're, things like water. Water is definitely more dense than a lot of materials. Not easy to compress. There's a bit of a gray area there. You can compress liquids, but not as much as a gas, but you can compress them a little bit more than a solid. Last but not least, gases, also fluids. They can form into any container that they are placed into. They're generally easy to compress. You guys have seen that before. You can compress a water bottle and shrink it down. You can shrink the volume of a water bottle. Eventually it gets difficult as the pressure increases, but you can compress gases quite easily. Low density, due to the particles being further apart, we say that gases in a container are low density. Think of something like a gas. If you can trap a gas, even if you could put it in a weightless container, think of a balloon. It's not quite weightless, but think of a balloon capturing gas. That is very low density. That would never sink on water. Some gases are so, have such low density that they also float in air, like helium. So that's molecular theory covered. Pretty, hopefully, review for most of you. Next up, what is temperature? We've all used thermometers before, but what is it? Temperature is a measure of the average random kinetic energy of the particles in a substance. There's a big blue word there, average. That is very important for the simple reason that it's an average reading. First of all, that average implies that not every particle is going to be traveling at the exact same speed. We know that particles are colliding with each other, and it's pretty chaotic. There's no way to say that each and every molecule or particle has the exact same kinetic energy, right? And if you recall kinetic energy, that is referring to basically any mass in motion. So even a particle, even though it's a small mass, a particle in motion is kinetic energy. So temperature is sort of an average. Very important to note that. If you do not mention that it is an average, you will not be awarded full marks for a definition because it is an average. Another good way to remember that it's an average is that it doesn't matter how big the substance is that you're measuring. When you stick your thermometer into something, picture you heat up a tea kettle and you've got this big pitcher of very hot water. If I pour a small amount into a coffee cup or I pour a large amount into a coffee cup, when I stick the thermometer in, I should get the same reading. Assuming I do it quickly, I'm not talking about letting either one cool down. Or I could stick the thermometer directly into the kettle, I should get the same reading. Basically, a liter of hot water, of tea kettle water, or 10 milliliters of tea kettle water. Either way, I should have some boiling hot water, and it's an average reading. So there's no advantage to measuring more of a substance or less of a substance. On that note of temperature, how do we know what's going on when two things interact? We always say that energy flows from hot to cold. Always repeat that in your brain. It is very, very important to remember. If you do not remember this, you will make silly mistakes on a test or an exam. The reason it's important to remember this is because we use cold as a description, and same with hot. We use it as a description or a sensation or a feeling, when in reality, heat is clearly, we're talking about some energy or some thermal energy, whereas cold is not really a thing in a physical sense. When something is cold, it just means it has less thermal energy, or it means it has less heat. Thermal energy and heat are essentially interchangeable. This is what we would call heat. So are things really cold? No, they're actually not cold if you wanted to be super scientific about it. Things are not cold. They just contain less heat. That's important. Temperature measures kinetic energy on average of the particles. More movement, more speed on average in the particles of a hot substance. Faster moving molecules, yes, collide into slower moving molecules. That is slowing down the fast molecules at the same time as it speeds up the slow moving molecules. So it's a lot to think about, but that's basically always happening around us at all times. Things are always trying to achieve thermal equilibrium. Let's move on to the specifics of temperature. We know it's an average measurement of the kinetic energy in the particles. Celsius is a very common metric measurement for temperature. Okay, we use this scale, and it's so popular, especially, like I said, anywhere that's using metric will probably use Celsius. It's so popular because water is a vital thing for all of biology, all of humanity. We ourselves are made of mostly water. So using water as sort of a benchmark is not the craziest thing. So we use water basically to determine this Celcius scale. You could actually make one of these quite easily. We look at the boiling point of water. We gave that a value of 100. We look at the freezing point of water. We gave that a value of 0. So we now have a scale from 0 to 100, and that's great. It goes from freezing to boiling. That's great for water. We know that other things can achieve temperatures much higher than that, and also much colder than 0 degrees. So of course the scale stretches on. But that is basically how we came up with this scale. That 0 to 100 divided into equal increments would yield your standard thermometer. You can do this, like I said. Old thermometers had mercury, that red liquid inside. Now it's usually some sort of alcohol with dye in it. But you can make a thermometer quite easily. Mark that line where freezing water seems to shrink down the mercury or the alcohol. Mark that. Why would that happen? Well, the substance would sort of shrink down because it is moving less, it's being cooled down. The ice would be absorbing energy from it, and it would shrink down to that set volume, right? Just like a solid becoming more tightly packed, or it's still a liquid, but it would just be getting more tightly packed. And then boil water. Now we've already got this marker at the freezing point. If we put it under, boiling water, we would see that this liquid would expand due to the molecules being excited by the thermal energy, and we would reach 100. By each one of those marks, you then could just divide it into equal increments, and then you've sort of got your temperature scale. So that's how Celsius came to be. But then came along Lord Kelvin, who came up with a temperature scale that is useful for one very simple reason. Kelvin is directly proportional to the average random kinetic energy of the particles in a substance. So in some ways, each Kelvin will be the same as each degree Celsius. What I mean by that is going up 1 Kelvin, going up 1 Kelvin is the same as going up 1 degree Celsius. However, there's something very advantageous about Kelvin. We use Kelvin, and the reason it is so advantageous to use is that we have this calculated, tested, coldest value possible, imaginable. And it is that we give the value of 0. So for the Celsius scale, we use 0 as 0 Celsius. The freezing point of water. That doesn't make useful when you think about it, because 0 Celsius doesn't mean it has 0 energy. That's impossible, right? Molecules, particles, they're always vibrating. They have some kinetic energy. So saying that, a block of ice has no energy in it, okay, that doesn't make a lot of sense. So now we're imagining the coldest possible temperature, and we're going to call that one 0 Kelvin. We don't use degrees, we just say 0 Kelvin. How cold is that in Celsius? It is negative 273 degrees Celsius. So the conversion is quite simple. We can do one quick example, and it is not difficult at all. You've just got to remember that when someone says that something is, it's cold outside, it's only 3 degrees Celsius. Well, think about that. Think of how much colder it could be. So giving that a value of 3 doesn't make a lot of sense. In reality, 3 degrees Celsius, there's tons of energy around there. Let's convert it to Kelvin. So in Kelvin, we would have 276 Kelvin. Now we're dealing with large numbers. So these common room temperatures, 21, 22, 17, these small numbers might be nice to deal with, but in reality, a 20-degree object has loads of energy. It is very far from the actual minimum that is achievable in the universe. We really know that there are other things that are much, much colder out there. So saying that, it's cold out today, it's only 3 degrees Celsius, there's actually tons of energy in objects that are 3 degrees Celsius. Tons of energy. So the the Kelvin scale is very advantageous because it's basically from 0 and upwards. I'm going to put infinity, of course. Reaching an infinite temperature is not possible, even if I reduce that to something you can wrap your brain around, something like 1,000 Kelvin. Going from 0 to 1,000 makes sense because, like I said previously, cold is not really a thing. Cold is not really a thing. You can just have less heat. Cold is a feeling, but it's not really a physical quantity. So the Kelvin scale is a good way to demonstrate that. You can just have lots of heat, you can have sort of a medium amount of heat, or you could have no heat. But at the end of the day, you can't really go lower than no heat. That just doesn't make any sense.